All right, this video is going to be on two different tests that we can use to see if a series will converge or diverge. So we're going to do the integral test and the P series test. So first we're going to talk about the integral test. So if f is positive, continuous, and decreasing, for x is greater than or equal to 1, and a sub n equals f of n, then the summation from 1 to infinity of a sub n and the integral from 1 to infinity of f of x either both converge or both diverge. So we're going to do a couple examples of this. The instructions are going to say determine whether the sequence converges or diverges. Or not the sequence, sorry, the series. All right, so for our first example, we're going to look at the summation from 1 to infinity of n divided by n squared plus 1. So I want you guys to be able to compare this with the series that we've looked at in the past where we used whether or not they were geometric or telescoping, and we used the Nth Term Test. So I want you guys to kind of think about those tests as we learn these new ones. So if we were to write out the first couple terms, we would get 1 over 1 squared plus 1, so that's 1 over 2. 2 over 2 squared plus 1 is 5. 3 over 3 squared plus 1 is 10. 4 over 4 squared plus 1 is 17, and so on. So if you look at these numbers, this is definitely not geometric. It's not telescoping. If we were to do the nth term test, you would be taking the limit of this, and the limit of this would be 0 because you'd have infinity on the top and infinity squared on the bottom, so you'd say the limit is 0. The nth term test is only going to tell you if the function diverges or if the series diverges, not if it converges. And you can only say it diverges if the limit as n goes to infinity is not 0. So here we're not going to learn anything about this because the limit is 0, and that was when the test was inconclusive. So the nth term test is not a good test for this situation. So that means we're going to use the integral test. All right, so if you do the integral test, we're going to go ahead and take the integral of this sequence, but we're going to write it as a function instead. And I'm going to integrate the function and look at it, evaluate it from 1 to infinity. And as you can tell, that's an improper integral. So that means that when we evaluate an improper integral, we're going to integrate it first, and then we're going to evaluate it using limits. So to integrate this, I do have to do u substitution. So my u is x squared plus 1. My du, the derivative of that would be 2x dx. I don't see a 2 in the problem, so that means I have to divide the 2 out in the front. So I'm going to be integrating and take 1/2 times the integral of 1 over u du. So that gives me 1/2 ln of u which is 1/2 ln of x squared plus 1. So that's what my integral was. I'm evaluating this from 1 to infinity, and as soon as I see that, I know that I need to use limits. So the limit as c goes to infinity of 1/2 ln, and that would be c squared plus 1, minus 1/2 ln of 1 squared plus 1. And that should have been an absolute value sign. That's my bad. All right, so as you plug in infinity ln of a huge number, if you were to look at the graph, it goes up forever. So this is actually infinity right here. And then here, this would just be minus 1/2 ln of 2, whatever that is. So here we would say that this is going to diverge because of that infinity right there. So that's what we got from the integral test, because it wasn't geometric, it wasn't telescoping, and the nth term test was inconclusive for us. It didn't give us enough information. All right, our second example is going to be to see whether the series 1 over n squared plus 1 converges or diverges. So if I look at this, the first term would be 1 over 2, the second term would be 1 over 5, the third term would be 1 over 10, the fourth term would be 1 over 17. So it's very similar to the last pattern that we have, we just don't have the n on top. So it's just 1 on top every time. So here again, I'm going to conclude this is not geometric or telescoping. If I were to try to do the nth term test, if I did the limit as n goes to infinity of this, I would find that that limit was 0. If it equals 0, that's when the test is inconclusive. So the nth term test is not helpful for us. So that makes this an integral test. So now we're going to be integrating 1 over x squared plus 1. And if you guys remember, this is one of those yellow sheet problems that we've done. So this is like, I think it's a squared plus u squared that you can see on the bottom, but in this case our a value would be 1, our u value would be x. So in the front, I don't have the sheet in front of me, I think it's like 1 over a in the front. Either way, there's not going to be a number in the front, and then it's a tan inverse of u divided by a, which in this case would just be x divided by 1. And this is going to be evaluated from 1 to infinity. And since this is an improper integral, we have to go ahead and do limits for this. So I'm going to say the limit as c goes to infinity of tan inverse of c minus tan inverse of 1. So you might not be very familiar with tan inverse functions, but if you go ahead and graph this, it looks like that. So if you remember what actual tan functions look like, they are this, but like straight up, so they go like that, and they have asymptotes. And the asymptote for a tan function, if you think about your unit circle, the asymptote for a tan function happens when you have y divided by x is undefined. So we're going to talk about this real quick. So here's my unit circle. So if I think, here's my points, I've got the point 1, 0, 0, 1, negative 1, 0, 0, negative 1. I don't think I can write on this. I have to I can't write on that. It's plastic. So if we think about how the tan functions work, it's y divided by x. It's where the asymptote is where it's undefined. So y divided by x is undefined. Up here at pi halves, that's 1 divided by 0. So when you do the tan inverse function, that horizontal asymptote is in the same spot where the vertical asymptote was. That means we have a horizontal asymptote at pi halves. The reason you should care about that is because as c goes to infinity, or as our x value goes to infinity, you're going to get closer and closer to that horizontal asymptote. So tan inverse of infinity is actually pi halves. And I can see that because I know about graphs and I know about the unit circle. That's how I was able to think through that. Tan inverse of 1, if I plug 1 in, I'm going to find, I want to say it's pi fourths. So 0.784, and then I'll just double check, pi fourths. All right, so pi halves minus pi fourths is going to be pi fourths, so this converges. All right, the other test that we're going to look at is the P series test. So the P series test works if you're looking at functions where it's 1 divided by n, whatever the term is, to the p power. So this would be 1 over 1 to the p plus 1 over 2 to the p plus 1 over 3 to the p plus 1 over 4 to the p. That was an exponent. And so on. So the p-value here is a positive constant. So the power of p is not a variable, it's going to actually be a constant, it's positive. So if the p-value is greater than 1, if this is like n squared, or n to the 1.3, or n to the 7/5, if p is greater than 1, then it's going to converge. If the p-value is between 0 and 1, then it diverges. So again, you can't have a p-value less than 0 because then it wouldn't be a positive constant. All right, so we do have a special case. It fits with these rules right here, but it does have a special name. It's called the Harmonic P Series.
You don't seem to have an app named P Series. We could see if the App Store has it.
Thank you, Siri. So the special case, the Harmonic P Series, is when p equals 1 exactly. So that fits here. We already know that it's going to diverge because it fits this information. So the Harmonic P Series, the most simple case would be 1 over n, although it could be like 3 over n, or 4 over n, or 7 over n, or negative 2 over n, or whatever. So this would be 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4, etc. And based off this, we're going to say it diverges. So again, it fits that information. It just has its own special name. All right, so here are 2 more examples. I think there's only 2 more examples. Instructions are the same, so we're going to determine whether the series converges or diverges. And this problem is 3 over n. So the first term would be 3 over 1, then 3 over 2, then 3 over 3, 3 over 4, etc. So if you look at this, you can see this is definitely not geometric or telescoping. If you were to do the nth term test, you would look at the limit as n goes to infinity. Again, the limit here would be 0. That's when the nth term test is inconclusive, so that's not helpful to us. You might actually be able to evaluate this using the integral test. However, what we're concerned with is that this is a harmonic P series. So we can look at that and we can see that it's in the form of a P series. So it's n to an exponent on the bottom. That exponent happens to be 1. So we're going to say this is a harmonic P series. And so that means, since p is 1, that the p-value is less than or equal to 1, which means it diverges. All right, and then last example, we're going to say we're looking at the series 1 over n squared. So that'd be 1 over 1, 1 over 4, 1 over 9, 1 over 16. If you look at this, it's not geometric or telescoping. If you were to do the nth term test on it, the limit as n goes to infinity of this would be 0. That's when it was inconclusive, so that's not helpful. We recognize that this fits a P series. And we know that the p-value is 2. And if we look up here, anytime p is greater than 1, this converges. So since p is 2, that means that p is greater than 1, and so it converges. We're not saying what it converges to, we're just saying that it converges.